Welcome to this lecture on metric spaces. Today we are going to explore one of the most beautiful and foundational ideas in mathematics known as Cantor's intersection theorem. Imagine you are trying to locate a hidden treasure using a very precise GPS system. First, it narrows the search to a country, then a state, a city, a neighborhood, and finally a tiny box. If you keep shrinking this search area, you will eventually pinpoint exactly one unique spot. This intuitive idea is exactly what Cantor's theorem proves mathematically. Let us dive in and see how it works. Before we look at the formal mathematics, let us understand why this concept matters. In advanced mathematics, we often need to prove that a specific solution or point actually exists, even if we cannot calculate it directly. Think back to our GPS analogy. If you keep trapping a space inside smaller and smaller boundaries, and the physical size of that space keeps shrinking closer and closer to zero, common sense tells us you will eventually trap exactly one single point. Cantor's theorem takes this simple, real-world logic and turns it into a rigorous mathematical guarantee, provided our space has no missing pieces or holes. Now that we understand the intuition, let us look at the formal statement of Cantor's intersection theorem. The theorem gives us a foolproof way to guarantee that a specific point exists, but it requires a few strict conditions. First, we must be working inside a complete metric space. A complete space simply means there are no missing points or gaps. It is solid. Second, we need a sequence of subsets that are closed, meaning they include their solid boundary edges, and they must be non-empty. Third, these sets must be nested inside one another. And finally, their maximum width or diameter must shrink to zero. If all these are met, their intersection contains exactly one point. This brings us to the mathematical notation for our sets. We represent our sequence of nested sets using the superset symbol. The formula shows that the first set, F1, completely contains the second set, F2. In turn, F2 contains the third set, F3. And this nesting continues infinitely for every set Fn. Conceptually, this is the mathematical equivalent of zooming in on a map. Each set Fn is a closed set, meaning it contains all of its boundary points, and none of them are empty. As the index n increases, we are moving deeper and deeper into our nested sequence, restricting our search area more and more. Now that we have our nested sets, we need to express the idea that they are shrinking to nothing. We do this using the limit of the diameter. The symbol delta of Fn represents the diameter of the set Fn. In a metric space, the diameter is simply the largest possible distance between any 2 points inside that specific set. The formula states that as n approaches infinity, this maximum distance equals 0. Physically, this means that as we go deeper into our sequence, the sets are getting infinitely small. Because they are shrinking down to absolutely nothing, they must be squeezing tightly around something, which sets the stage for finding our unique point. Before we move on to an example, let us see this with a concrete visual. Here, you are looking at a sequence of nested closed sets on a number line. Notice the top line segment, F1, it is the largest. Completely inside its horizontal boundaries is F2. Then F3, and so on. The vertical dashed lines clearly show how each subsequent set is trapped inside the previous one. As we move down to F5, the length of the segment, which is its diameter, is shrinking. If we continued this infinitely, the diameter would become 0, squeezing down perfectly onto that single unique point labeled x on the axis. This diagram perfectly captures the essence of Cantor's theorem. Now that we have visualized the concept, let us see this with a concrete example. We want to show how Cantor's theorem works in a real, everyday math scenario. We are given a sequence of closed intervals on the standard real number line, defined as Fn equals the closed interval from 0 to 1 over n. Our goal is to verify that all conditions of the theorem are met. Let us write out the first few sets to clearly see what is happening. The first set, F1, contains all numbers from 0 to 1. The second set, F2, is from 0 to 1 half. The third is from 0 to 1 third. Because we use square brackets, they include their exact boundary endpoints, proving they are closed sets. Continuing with our example, we must verify the remaining conditions. First, we check for nesting. Since the interval from 0 to 1 half is completely contained inside 0 to 1 and 0 to 1 third is inside 0 to 1 half, we can confidently say the sets are nested. Next, we need to find the diameter of these sets. On the real number line, the diameter of an interval is simply the larger endpoint minus the smaller endpoint. So 1 over n minus 0 gives a diameter of 1 over n. Finally, we take the limit as n approaches infinity. As the denominator grows infinitely large, the fraction 1 over n shrinks down to exactly 0. The size condition is perfectly satisfied. Because all the conditions of Cantor's theorem are met, we are absolutely guaranteed to find exactly one point at the final intersection. Let us find it. Looking at our intervals, the number 0 is the left endpoint of every single set, so it is always included. What about other numbers? Any number slightly larger than 0 will eventually be excluded because the right endpoint, 1 over n, will eventually shrink past it. Therefore, the single unique point trapped in the intersection is exactly 0. This perfectly demonstrates how the theorem pinpoints a single location. It is crucial to understand why every single rule in a theorem matters. What happens if our sets are not closed? Let us look at a second example, using open intervals, written with round parentheses. The set Fn is the open interval from 0 to 1 over n. This means they contain all numbers strictly between 0 and 1 over n, but they do not include the exact boundary numbers. They are still perfectly nested, and just like before, the diameter is 1 over n, which shrinks to 0. So the size condition is satisfied. However, because they lack their boundary edges, they are not closed sets. Let us see how this breaks the theorem. Here is where the entire process breaks down and fails. We are looking for a number that exists inside every single set in the sequence. The number 0 is not in any set because the round parenthesis means 0 is strictly excluded. If we pick a tiny positive number like 0.001, eventually the fraction 1 over n will become smaller than that, meaning our tiny number gets left out of the later sets. Because the sets are not closed, the point we are trying to trap slips through the missing boundary. This leaves the final intersection completely empty. This proves why the closed set condition is absolutely necessary. Now that we have successfully used the formulas and seen examples, let us understand why this theorem works by proving it step by step. We start by picking one arbitrary point from each set to create a sequence of points. We choose xn from the set fn. Because the sets are nested, if we look at any 2 points, xn and xm, chosen after a certain stage n, both of those points must actually live inside the set fn. Therefore, the distance between them must be less than or equal to the diameter of fn. Since we know the diameter shrinks to 0, the distance between our points also shrinks to 0. This makes our sequence a Cauchy sequence, meaning the points are bunching up infinitely close together. Continuing with our proof, we now use the completeness of the space. Because we stated at the very beginning that our overall space is a complete metric space, we are guaranteed that every Cauchy sequence must settle down and converge to a real existing point. We will call this final destination point X. Completeness is the magic ingredient here. It ensures the target point is actually there and not a hole. Now, for any fixed number n, all the points in our sequence from xn onwards are trapped inside the set fn. Because fn is a closed set, it contains all its limit points. This means the final destination x of this trapped sequence must also be inside Fn. We have shown that x is in Fn for every single set, so it must be in their exact overlapping center, the intersection. Finally, we must prove that x is the only point in this intersection. Let us pretend there is a second point, y, that is also trapped in all the sets. If both x and y are inside every set Fn, then the distance between them cannot be larger than the diameter of Fn. But we know the diameter shrinks to exactly 0 as we go to infinity. Therefore, the distance between x and y must be 0, which means x and y are actually the exact same point. We have successfully proven that exactly one unique point exists. To wrap up, let us review the most important ideas we have covered. Cantor's intersection theorem is a powerful guarantee about trapping points in a complete space. It tells us that shrinking, nested, closed sets will perfectly pinpoint exactly one location. Remember how the conditions connect? The completeness of the space ensures the point actually exists, while the closed nature of the sets prevents the point from slipping through the boundary. This foundational pillar is what proves the real number line has no gaps, allowing calculus to work smoothly. You have now mastered the full concept, from intuition to rigorous proof. Excellent work!